Good afternoon, everybody. Thanks for tuning in for our next installment of the Urban Water Innovation Network Science Talk webinar series. These presentations focus on key findings of our 5-year research projects with an emphasis on pragmatic recommendations for stakeholders and practitioners. Today, we're shifting gears and kicking off Research Thrust B, using data, models, and enhanced process understanding from Thrust A, the impacts of innovative technological solutions on sustainability of urban water systems across eco-hydrologic regions are examined under Thrust B. As you probably know, we are recording each of these webinars, and I'll be posting those videos to our YouTube channel on the UN website. All participants should have entered the webinar muted, but we do hope to engage our listeners with questions and discussions at the end of the presentation. So feel free to use the chat queue or turn your mic and webcam on at the end of the presentation. So with that, I'm excited to introduce Dr. Ali Mostafavi, Associate Professor of Civil and Environmental Engineering at Texas A&M University. Ali's research interests include urban resilience, networks and complex systems, urban computing, disaster informatics, and applied artificial intelligence. So Ali, thank you for joining us today. I'm going to hand the controls over to you.
Sure. Thanks for the great introduction, Sarah. Thanks everybody for joining this webinar. Today I'm very excited to talk about one of the studies we conducted as part of our project within the UWIN network, focusing on exploratory assessment of adaptation planning when it comes to water supply infrastructure and their resilience enhancement, specifically in the case of sea level rise impacts in coastal areas. Before I start, I would like to acknowledge my former doctoral students, Kambiz Rasul Khani, who led this study and was the lead researcher on this project for our UWIN work. What we present today is essentially to demonstrate the need and application of using newer approaches and models to inform adaptation planning and decision making when we are dealing with really complex planning decisions and action planning when it comes to dealing with climate change impacts and stressors that water infrastructure and water systems endure over the next several years. And the takeaway for this presentation that I hope everybody gets by the end is the value of such exploratory assessment and model-based tools for decision-making and adaptation planning to enhance decision-making under deep uncertainty, which is a very active field of research, especially in water resource management. So the work that we present specifically deals with the issue of sea level rise and its impact on water supply infrastructure in coastal communities. Many of the coastal communities, specifically in the US, are dealing with issues of sea level rise that affects their water supply. Why? Because most of these communities are relying on underground water for their water resource supply, and saltwater intrusion is caused or exacerbated by sea level rise. So, and these are the things that I learned from my dear colleague, Dr. Suka, who is on the webinar today, that this increase in sea level rise and depletion of groundwater creates this hydraulic difference that accelerates the saltwater intrusion into the aquifers. And this salination and increased salination reduces the capacity of or availability of fresh water supply, and it requires making decisions and taking actions for dealing with this, either to change the location of the well fields to take them further away from the salinity lines, or increasing the capacity of the treatment plants so that they can have desalination technologies to remove salt water from the groundwater. But these adaptation actions, whatever they are, they require assessments and evaluation of when they should be implemented and how they should be implemented so that they are effective and reduce the impacts of these events over the long term. In addition to this chronic creepage or intrusion of salt water because of the sea level rise, we have another phenomena that is happening during a storm surge event, which is the Overwatch intrusion that happens when we have the seawater that is coming through the storm surge and intrudes into the groundwater, and that's another mechanism of saltwater intrusion. So thinking about, let's say, a 50-year horizon, and thinking about a coastal community that relies on groundwater, their water supply is threatened by two stressors. One is more chronic, which is creeping this seawater into the groundwater, and one is more acute, which is the Overwatch, when we have hurricanes, and we see that we have more frequent hurricanes with more extensive wind speeds that increases the likelihood of these storm surges, and as a result of that, the Overwatch saltwater intrusion. So the question is, when we are thinking about the 50-year horizon, what actions need to be taken to reduce the long-term impacts of these events and improve the resilience of the water supply infrastructure? And by resilience, we can simply think about the ability of the water supply infrastructure to supply the demand of the communities over a long term. And these questions are very important, at the same time complex, because we cannot just think about, okay, we will have this level of saltwater intrusion every year, and based on the distance of the wells from the salinity line, at this time we will expect the intrusion. Therefore, we can plan ahead and start mitigation and adaptation actions at this point. The problem is we have uncertainty. So there are, based on IPCC projections, we have different projections for sea level rise, slow, medium, high projections, that is still there is no certainty about which one is more likely over the next 50 to 100 years. So there is uncertainty on that. And when you translate this sea level rise scenarios into groundwater saltwater intrusion, there is uncertainty in that as well, depending on the level of groundwater, the type of soil, and other characteristics. The rate of intrusion would vary. So we will have different scenarios of sea level rise, plus different scenarios of saltwater intrusion under different scenarios. So this creates uncertainty. Another source of uncertainty is the aging of infrastructure and how the infrastructure will perform over the next 50 years, because the agencies and people who make decisions now will not be most likely be the decision makers in 20 or 25 years. So we have the uncertainty about what type of decision will be made over the life of or over the analysis horizon that affect the performance of infrastructure. And these sources of uncertainties and complexities usually lead to what is undesirable, which is inaction. So and inaction means kicking the can down the road, waiting until we have more perfect information to make decision and to make adaptation investment, which are very costly. And thinking about just making adaptation investments, like moving the wells or adding desalination technologies to treatment plants, etc. All of these require significant investments. And under the uncertainty, one of the adverse effects of uncertainty is this decision paralysis and just kicking the can down the road in a hope that we have a more perfect information. And that's where this idea of using more advanced methods and models come into play. Models that not only can inform about the stressors and what would be the projections of different stressors and the scenarios that could happen, but also the performance of infrastructure under those conditions, and also the decision-making behaviors of the different actors, whose decisions lead to actions, and the actions lead to changes in performance of infrastructure under different scenarios. Because of that, we are proposing this kind of thinking on complex system view for decision making when it comes to adaptation planning for dealing with sea level rise and climate change impacts on infrastructure. We showed a demonstration of such models in the case of saltwater intrusion problem and sea level rise on water supply infrastructure. But the application of these types of models for decision making is broader than that, and it could be applied in other domains and problems in water resources, and other colleagues in other universities and research institutes that also have demonstrated that. So in this type of complex system thinking, we're looking into three components. We look into the climatic hazards, the saltwater intrusion, the sea level rise scenarios, the human actors who make decisions, and also the physical infrastructure and the complex processes and interactions between them. So just as an example, when we have saltwater intrusion and sea level rise scenarios, the human actors perceive the risk, and based on the risk perception, they make adaptation actions. And the adaptation actions changes the characteristics of physical infrastructure, whether it's the location of the well fields that changes the vulnerability of the well fields to the salinity, hazards, or the capacity of the treatment plants for desalinating the water when it's has salt in it. And the performance of physical infrastructure is, of course, affected by those chronic stressors. And the combination of these interactions, determines the overall performance and availability of water over the long horizon. And again, we're thinking about like 50-year decision horizon or 100-year. And this type of decision, when the decision horizon extends, the uncertainty expands, and because the uncertainty expands, this decision paralysis or inaction is more prominent. So the benefit of these types of models and analysis is that it can help identifying different scenarios, evaluate the effect of different decisions and actions and their effectiveness under different scenarios, so that it can inform decision making now and inform adaptation planning and action. So I go ahead and demonstrate the model and its component that we developed in the context of sea level rise impacts on water supply infrastructure in coastal communities, and talk about how we model each of these components, the climatic hazards, human actors, and physical infrastructure and their interactions, and create a complex system model that provides a decision dashboard that decision makers and planners can evaluate different scenarios. What would happen if you have slow scenario of sea level rise with more faster saltwater intrusion? What would be the metric of interest, which is availability of water supply for the community, be in 50 years? And what would be the instances that the salination extent is reducing our capacity to provide fresh water for the community? So the first component is the focus on hazard and the climatic stressors. So we model this complex system model in a multi-agent platform, and we consider each of those components as an agent class, so that we can model the underlying complex behaviors and processes and mechanisms corresponding to each of those components. So the first component is hazard agent or climate stressors agents. As I mentioned, we have two components of uncertainty here. One is the projection of sea level rise scenario, which is, as I mentioned, our source of information is the IPCC's projections of sea level rise scenarios, low, moderate, and fast sea level rise. And under each of them, based on groundwater models, we can have different scenarios of saltwater intrusion. So under the slow sea level rise, we can have the slow case of intrusion, moderate case of intrusion, and fast case of intrusion. And these are coming from a physics-based groundwater models. And we adopted the outcomes of the models that were already implemented in our study testbed, which is Southeast Florida, that I'll talk a little bit more later. And as you can see, there are different projections. So the solid line at the top shows the fast sea level rise and fast saltwater intrusion. You can see that over 100-year horizon, the number of feet of intrusion exponentially increases. And then the best case is the slow sea level rise and the slow saltwater intrusion that over 100 years will lead to around 50 to 60 feet of intrusion. And there is uncertainty. So the range of outcomes vary, as you can see, from 60, 80 feet of intrusion over 100 years to 10,000 or 12,000 feet of intrusion. And as a decision maker, as a planner, this wide uncertainty can be confusing. So we need to translate these outcomes. So one way is just overlay these scenarios on the existing condition of infrastructure and say, oh, okay, which assets would be vulnerable under each scenario? But this type of static assessment does not help us evaluate scenarios. So we have to have elements so that we can see the decisions that could be made, the outcome of those decisions in terms of adaptation actions, the outcome of adaptation actions in terms of changes in the physical infrastructure, and then the changes of physical infrastructure in terms of the capacity to provide the supply of water to the community. So because of that, the second component of our work focuses on the actors. But as I mentioned, before I go to the actors component, the second, another stressors that is caused by sea level rise is exacerbated overwatch intrusion, which happens during the storm surges. And the way we model that in our model, just quickly, I don't want to go through the math and mathematical aspect of it, just wanted to show how we can integrate different models and processes together in one complex system model. We use this Poisson process that models the frequency of storm surges happening based on the historical records and based on each instance of Poisson process simulation. For example, over 100 years, we might have like 10 of those storm surges. In one scenario, we might have 20 of those. In one scenario, we might have 5 of those. So using this Poisson process, we can model thousands of scenarios to see the instances and timings of those storm surges. And then based on a storm surge, we can translate the storm surge to acceleration in the intrusion of the salt water into the well fields. And then the total saltwater intrusion is determined by the chronic one from the previous model, plus the ones that are modeled based on this Poisson process. And the outcome of this will be an input to the second component of our model, which is the utility agent or the actor. And basically, again, I don't go to the details of the model, but this is following the same process that the decisions are made. So the salinity line is monitored, and based on the location of the salinity line and the decision horizon, for example, if the decision horizon is 5 years, and the agency sees that based on the current rate of intrusion and anticipated rate of intrusion, the wells will not be contaminated over the next 5 to 10 years, they might wait and implement any adaptation actions later so that more information is available. So there are two approaches that can be taught here. One is an adaptive planning approach that is essentially thinking about the future, what could happen, and proactively make adaptation actions before adverse effects are observed. And the other approach is a reactive approach that is essentially what's going on these days, which is essentially look for what is happening and reactively adapt. For example, if there is salinity in the water, improve the desalination capacity. So one of the powerful aspects of these types of analysis is the ability to see the benefits of adaptive planning, how much cost they could help us save, and how effective they could be when juxtaposing the outcomes with the outcomes coming from the reactive approach. So in order to model the decision-making processes of actors, we also have to account for the decision-making behaviors, and we relied on decision theoretic models. And there are two important decision theoretic models that we adopt in this study. One is the theory of bounded rationality, which is under imperfect information and confined time, and really limited resources, actors are looking for more satisfactory solutions rather than more optimal solutions. And that's what essentially bounded rationality is. So essentially at each decision point, let's say at time now when the planning is happening, based on different scenarios of sea level rise that can happen, different saltwater intrusion scenarios that can happen, the agency anticipates whether the existing well fields will experience any intrusion, and then based on their risk attitude, whether it's a risk seeker, risk neutral, or risk averse attitude, they make decision whether to wait, whether to implement any adaptation action. So the good thing about it is that we can use models to model these decision-making processes, and also have the risk attitude of the agencies be updated based on the information. So for example, if they decide to wait and then in the next planning point, they see that they're, let's say they were risk seeker in the previous planning point, they can update and become more risk averse or risk neutral. And with this, we could model the risk attitude of the agency, which is an important aspect of decision making under uncertainty. The second component of the modeling of the actors' decision making is, of course, the selection of adaptation actions and also the decision making on the risk. And we leverage the advances in theory of regret aversion. So essentially, based on prospect theory, under uncertainty, human decision makers try to minimize their regret, or they try to show a risk averse behavior. So we asked ourselves what would be a risk averse behavior in the context of adaptation planning, and essentially it would be consider all possible scenarios and then see what would be the maximum risk that the system could experience and minimize the maximum risk. And to minimize the maximum risk, there are different adaptation measures that are available. So we considered in this study 4 different types of adaptation actions: either an aquifer recharge, or constructing salinity barriers, or relocating the well fields, and also improving the desalination technologies in the existing facilities. There are costs associated with each of them that we estimated based on input from different agencies in the area. And based on the cost, they also have certain efficacy. So some of them are efficient in pushing, having a longer term effect on the water supply availability, and some of them are more short term decisions. And it depends on the scenarios that would happen. And the model that we created enables capturing all of this: the risk attitude of the agency, the hazard perception that they have, and then the actions they make. So essentially what this figure at the top shows is at each decision point, based on the risk attitude of the agency and their perception of the hazard, for example, whether the sea level rise would be slow for the next 5 to 10 years, and what would be the projection of saltwater intrusion, then this would be the input into the regret aversion model. And based on the regret aversion model and the availability of funding, they select the adaptation actions, whether to do nothing or select one or multiple of these adaptation actions. The results of adaptation actions will change the attributes of infrastructure systems, and then based on what actually happens, we will see whether the decisions were efficient or not. So, and this process occurs at all points in time. So for the interest of time, I won't go through the details again, the mathematical details of the regret aversion theory, but the essence of that is, if you want to improve, if our metric of interest is the level of service, which is the supply capacity over projected demand over the 100 years, we want to have always 100% capacity for the projected demand. So under each adaptation actions and under each scenario of sea level rise and saltwater intrusion, we will have different outcomes. So, and based on the risk attitude of the agency, we will have optimistic, most likely, and pessimistic outcomes. And essentially, based on regret aversion theory, the decision is made based on the scenario that minimizes the maximum regret. So we calculate the maximum, we create a regret matrix, and based on that, calculate the maximum regret, and then try to minimize the maximum regret, which would determine what actions would be implemented at what point in time. So based on that, the outcomes of actors' decision making, we can determine the effects on the water supply infrastructure. So for example, in this case, the effect would be on the supply capacity of the water supply, which would be summation of the extracted water that they extract from the groundwater, plus the treatment capacity of the existing facility, plus any desalinated water that will be used in the system. So the projected demand is, of course, based on the base population and consumption per capita, plus the population growth that is expected in the region. And the metric of interest for the performance of the system, as I mentioned, is the supply capacity over projected demand. And based on that, we can simulate 100 years and see instances that the system is not capable of providing 100% capacity for the demand, and evaluate the results of the decision. So that was kind of like an overview, a brief overview of the components of the model. Let me now show our demonstration of application in the case of the Miami-Dade County. So the system that we are looking here in Southeast Florida, Miami-Dade County, has one decision agency, has 3 water well fields at this point, 3 water treatment plants, and 1 population area that all rely on the Biscayne aquifer. And the well fields information and their distance to the current saltwater intrusion line is determined. The population and the population growth expectations of the area is also listed here. And essentially, we use this information to ask the question of what type of adaptation actions need to be made at what time, based on how much investment to improve the long-term performance and resilience of the water supply system in Miami-Dade County. So this is kind of a snapshot of the output of the model. As you can see, we can have different parameters visualized. For example, the change in the risk attitude of the agency over time, the base case scenario in terms of the sea level rise scenarios that actually happened, what the agency would perceive, and also what adaptation actions would happen at what time. So this chart at the bottom, as you can see, the adaptation measure, you can see at the beginning, the focus in this scenario is more on aquifer recharge, but after that, salinity barrier, and later on is desalination. And this is kind of a more reactive approach to dealing with the scenario, and this is for a slow to moderate sea level rise scenario. And of course, for a faster sea level rise scenario, the situation would be different. So essentially, what we create is a decision model at the fingertips of planners, in which they can determine the different risk attitudes for decision making, different thresholds for activating actions. So, for example, they can say if the saltwater intrusion line reaches at, let's say, 5,000 feet of our current well fields, that's the time that that's a trigger point for us to start implementing an action. And that parameter could change, and they can see how sensitive the decisions and actions would be to that parameter. And other decision-making parameters, such as capital funding, how much capital funding would be available at each decision point, and to what extent the availability of funding could affect the long-term performance of the system. And in using these models, several scenarios can be simulated. And our goal is not predicting the future. Our goal here is to enable scenario evaluation, enable evaluating thousands of scenarios based on combination of different climate scenarios, different saltwater intrusion scenarios, different decision attributes, different adaptation actions, and see the outcomes, and then identify the timing of actions and type of actions that enable maximum performance across multiple scenarios. And we just did that. We identified the 4,158 possible scenarios based on different scenarios of sea level rise. We have 3 scenarios of sea level rise, 3 scenarios of saltwater intrusion, 3 states for risk attitude of the agency, different 11 levels of funding for different adaptation planning decision points, different decision intervals, and the combination of those just sums up to 10,000 scenarios for adaptive planning scenario, and for reactive planning scenario we will have 4,000 scenarios. So using this model, we simulated 14,000 different scenarios so that it can tell us how much funding we need, when the adaptation actions can be implemented, what type of adaptation actions need to be implemented, so that it can guide the adaptation planning in this really complex decision environment that we have so much uncertainty and so much complexity because of different characteristics of human decision making, infrastructure systems, and hazard characteristics. I show you some examples of the outcomes. So, for example, we can here see the difference between the importance of different parameters in decision making, in adaptive planning and reactive planning. As you can see, in reactive planning, the outcome of the performance of the system is more governed by how much saltwater intrusion we have, the actual saltwater intrusion scenario. But you can see that the effect of actual saltwater intrusion scenario is minimized in the adaptive planning. When we are planning adaptively, the state of the nature we are one step ahead of that. And regardless of what happens, we already have measures in place so that we can reduce the impact of that parameter on the overall performance of the system. Another thing we can see that the difference between the required capital funding or the importance of capital funding. So for adaptive planning, it's more important to have more funding because we are proactive. We are making actions under uncertainty. But for reactive planning, yes, in terms of capital funding, its importance is reduced, but the effectiveness of those investments are reduced as well. So the decision is whether we want to spend less and be less effective, or spend more and be more effective using adaptive planning. And essentially, this approach, this result shows the importance of adaptive planning. And adaptive planning cannot be done unless we use models like this. To evaluate scenarios, to generate scenarios, and to evaluate the outcome of the actions in each scenarios, and then select actions that are robust across different scenarios, not just one action that is the optimal action in a couple of scenarios. We want an action that is robust across multiple scenarios. And we cannot do that unless we generate those scenarios. And the generation of those scenarios is what these complex modeling approaches try to achieve. Another example of result is the overall long-term performance of the system, which we measure that using the long-term resilience index, which is the simple supply over demand ratio, and the probability of that using the reactive approach, which is the red line here, and the adaptive planning approach, which is the black line. So as you can see, the adaptive planning approach would have significant likelihood to lead to really high values of resilience index. But reactive approach, we might have varying levels of the resilience index, and this suggests that we can lose up to 40, 50, or 60% of our capacity to supply the water to the community if we follow a reactive approach and do not make decisions in a robust fashion. And this is another result that suggests adaptive planning and the importance of adaptive planning using these model-based adaptation planning frameworks. And the last set of results I want to show is related to the level of investment. So as you can see here, we have different levels of investments needed at different years and under different scenarios of sea level rise. So essentially, if the scenario of sea level rise would be the fast sea level rise, of course we need more funding, right? But the benefit of adaptive planning is that more funding would be better spent when our approach is adaptive and the actions are more robust. And when we are reactive, we probably will spend the same amount of time, same amount of money, later, but they won't be as effective. So this suggests that there is a window of opportunity for adaptation. If we don't take that window of opportunity, in which our models show that it is for this case of Miami-Dade and the sea level rise scenario is the year of 2030. If we pass that window of opportunity, the adaptation would be more expensive and less effective. So we will probably invest more, but with less effectiveness on mitigating the impacts and improving the system performance. So this has implications about the next 10 years, the plans, adaptation plans, actions we make, and the effectiveness of those gets disseminated. And I'll go back to the first comment I made about the importance of these complex models and for decision making under uncertainty. Because of uncertainty, we kick the can down the road, we face decision paralysis and inaction. And it's very hard to justify millions or billions of dollars of investment while we don't see the impacts already. Even then we see the impacts. For example, when we see nuisance flooding on the streets of Miami Beach, it's a difficult justification for making investments for pump stations to pump the water back to the sea. But for the impacts that we still don't see, people don't still taste salty water in the tap water. It's difficult to justify those investments, and this will lead to inaction. And now with this result that we have a window of opportunity of, let's say, 10 years in this case, and if the plans and adaptation actions are not adaptive and proactive within these 10 years, then after that we have to spend more money and with less effectiveness. This will show the importance of these types of models for generating scenarios, for evaluating different scenarios and see the effects of different levels of investment and decision characteristics on the outcome. And I want to again emphasize that the purpose of this is not prediction. We don't want to predict exactly when saltwater intrusion happens, when certain well fields will be out of service. What we want to predict, what we want to provide is a decision tool so that we can generate, as you could see, 14,000 different scenarios, combinations of climatic hazards, saltwater intrusion scenarios, decision-making parameters such as decision attitudes, risk attitudes, level of funding, and infrastructure adaptation actions, the combination of them, and see how would that affect the long-term performance of the system. And we are talking about a long horizons, 50 to 100 years, and these types of models will inform planning much more effectively. And this is how the adaptation planning should be made. That's what we believe, and many scholars in the field of deep uncertainty, adaptation planning should be made for water infrastructure and other infrastructure in the face of climate change impacts, where we have significant uncertainty. So the traditional and conventional planning approaches are not adequate, and we need these complex modeling approaches for decision making. So with that, I'll thank the UWIN network and NSF for supporting our project, and I'd be happy to answer any questions you might have.
Thank you, Ali. I can't decide if your perspective is the glass is half full or half empty for the next 10 years. Maybe we just need to put some salt in that glass.
Yes.
Anybody have any questions? I'll throw one at you. This is a new tactic we're thinking about taking. If you had the opportunity to make a front page headline about your research, what would that headline be?
I think I would say it would be, this window of opportunity for adaptation planning. We have limited time to be proactive in making adaptation plans and investments. But after that, it will be more expensive and less effective. And I think that would be a headline.
Absolutely, I agree. I see something from Alex. Alex, do you want to turn your mic on, or do you want me to read this out loud? I'll go ahead and read it. On slide 16, do the importance levels interact at all, considering they're both weighted to be a percentage? Maybe I'll just let you read that, Ali, and see if
Sure. I think I understand the question. Great just to have you on the call, Alex. The importance level, we generated 14,000 scenarios, and based on these 14,000 scenarios, we had different levels of system performance and outcomes of the system. So we created these decision tree models, classification regression tree models out of this 14,000, and these will tell us how each parameter in the system in the model will affect the outcome. So these are based on how actually they will influence the outcome in across all the 14,000 scenarios. So the ones that are less important, for example, under the adaptive planning scenarios, the actual saltwater intrusion parameter is less important because in the decision tree it's at the lower levels of the decision tree. But in the reactive planning, it is the most important factor that affects the outcome, because what happens is we are not making proactive actions to eliminate the effects of the what the state of nature will impose on our system. So essentially, these importance levels are the outcomes of the scenarios that we simulated and use them in creation of these scenario landscape and where each parameter is located in the scenario landscape.
Thank you, and thanks for that question, Alex. You're always so interactive. We really appreciate that. Any other questions?
Hey, Ali. Well, thanks for this. It's really kind of fascinating. I think it's super important work. But I guess at the same time, I wonder how we've done in reaching the stakeholders on this. I assume you probably got this fully published now?
Yes, yes,
Yeah.
this is fully published, and that's Mike, I appreciate all the support you provided for this study. I think your input and expertise was foundational in not only developing the model but also validating it. So we validated the model with the stakeholders, but one of the things is this perception of stakeholders in terms of models, right? I think there is a gap, and I speak from perspective of both an instructor and researcher. We teach students that models are intended to be predictive and create predictive capabilities, and then we say that these models that or for adaptation planning, for example, are not intended for predictive purposes, but more for scenario analysis and scenario generation to evaluate different probabilities of different possibilities. And when I was thinking about what would be my takeaway message from this study is the need for these models. There should be more receptivity from stakeholders for using these models. I understand that the development of the significant amount of data goes into them. Sometimes the mathematics and the algorithms behind that capture different mechanisms and processes are a little bit complex to be communicated. But I think if these models are developed in a participatory way with the stakeholders involved, that's what we did. We engaged folks from Southeast Florida, water community, both from WASD and from the compact, and we incorporated their perspective. I think they will have more ownership of the model, and then they will have more receptivity to the outcomes. And and I think if it's done as part of the adaptation planning process, then it's a win-win situation for both researchers and also the stakeholders, and it will have much more dissemination and adoption in the planning process. But right now, I think the state of the practice is that there is not the penetration of this type of modeling and assessments are not significant. And what I see from the practitioner's perspective, not from the owner and operator side, but from engineering consulting side, there is a positive trend in companies such as Arab or Atkins, that they start offering services based on these complex system models, which is very, very promising, because this shows that research has informed engineering consulting, and engineering consulting can inform the owners and operators and other stakeholders. So the change is happening in terms of more receptivity to these models and the reach out to stakeholders. But still, I think we are thinking about planning like the conventional water resource planning, not thinking about a new class or new paradigm for adaptation planning, which is different from the standard way we do water resource planning.
Yeah, okay, so that seems consistent with what I kind of feel like is going on. I got to make sure I send those links back out to like Virginia Walsh and those people here, because it's really relevant locally. So
absolutely.
Thank you.
Thank you, Mike.
Any other questions from the team? And Ali, I'm sure it's recorded somewhere, but as a follow-up, if you just want to send me the DOI or the link for the publication, I can make sure that gets disseminated.
Absolutely. I'll send it right away after the webinar.
Great. Okay, well, hearing not much from the peanut gallery, in this day and age, I'm sure somebody has another meeting at the top of the hour and wouldn't mind an extra couple minutes to grab something to eat or just take a screen break. So thanks everyone for tuning in. Hope to see you next week, and I'll be sure to pass that link around so we can get this in the hands of people that need it. It's good to see you, Ali, and take care, everybody.
Thank you.
Thank you, everybody. Bye-bye.